Everyone's training the network all the time, is what it amounts to. Whether autopilot is on or off, the network is being trained.
I want to just get to your slam on LiDAR, because it was pretty clear you don't like LiDAR. And this
LiDAR is lame. LiDAR is lame. Lame.
That is true. What happens to the rest of the industry that's building their autonomy solutions on LiDAR?
I should point out that I don't actually super hate LiDAR as much as it may sound, but at SpaceX, SpaceX Dragon uses LiDAR to navigate to the space station and dock. Not only that, SpaceX developed its own LiDAR from scratch to do that, and I spearheaded that effort personally. Because in that scenario, LiDAR makes sense. And in cars, it's friggin' stupid.
Tesla Throwback Thursday. Today is just a simple continuation of Tesla's first Investor AI Day. If you missed class last week, you can check out part 1 here or here. I don't know. It shouldn't be hard to find. I'm pretty sure you can watch these in any order. Without further ado, let's get to it.
Because one thing to remember about our FSD computer is that it can run much more complex neural nets for much more precise image recognition. And to talk to you about how we actually get that image data and how we analyze them, we have our Senior Director of AI, Andrei Karpathy, who's going to explain all of that to you. Andrei has a PhD from Stanford University, where he studied computer science, focusing on vision recognition and deep learning.
Andrei, why don't you just do your own intro?
Exactly.
There's a lot of PhDs from Stanford. That's not important.
Yes.
Okay, we don't care. Andrei started the computer vision class at Stanford. That's much more significant. That's what matters. So can you please talk about your background a way that is not bashful? Just tell me about the stuff you've done. Yeah.
Just tell them why you're the best in this field and the authority in the space.
Yeah.
I think I've been training neural networks basically for what is now a decade. And these neural networks were not actually really used in the industry until maybe 5 or 6 years ago. So it's training a lot of neural networks, not just for images, but also for natural language, and designing architectures that couple those two modalities for my PhD. At Stanford, I actually taught the convolutional neural networks class, and so I was the primary instructor for that class. I actually started the course and designed the entire curriculum. So in the beginning, it was about 150 students, and then it grew to 700 students over the next 2 or 3 years.
I mean, Andrei is like really one of the best computer vision people in the world, arguably the best. Yeah.
So Pete told you all about the chip that we've designed that runs neural networks in the car. My team is responsible for training of these neural networks, and that includes all of data collection from the fleet, neural network training, and then some of the deployment onto that chip. What do the neural networks do exactly in the car? So what we are seeing here is a stream of videos from across the vehicle, across the car. These are 8 cameras that send us videos, and then these neural networks are looking at those videos and are processing them and making predictions about what they're seeing. And so some of the things that we're interested in and some of the things you're seeing on this visualization here are lane line markings, other objects, the distances to those objects, what we call drivable space, shown in blue, which is where the car is allowed to go, and a lot of other predictions like traffic lights, traffic signs, and so on.
Ladies and gentlemen, let me reiterate this. This is 4 years ago in April. Notice the rhetoric that Andrei is using? The neural networks are perceiving, predicting paths. We all know that technology advances at a rate that we can barely comprehend. But this was 4 years ago. Where do you think they are now?
I will talk roughly in 3 stages. So first, I'm going to give you a short primer on neural networks and how they work and how they're trained. And I need to do this because I need to explain in the second part why it is such a big deal that we have the fleet and why it's so important and why it's a key enabling factor to really training these neural networks and making them work effectively on the roads. And in the third stage, I'll talk about vision and LiDAR and how we can estimate depth just from vision alone. So the core problem that these networks are solving in the car is that of visual recognition. So for you and I, this is a very simple problem. You can look at all of these 4 images, and you can see that they contain a cello, a boat, an iguana, or scissors. So this is very simple and effortless for us. This is not the case for computers. And the reason for that is that these images are, to a computer, really just a massive grid of pixels. And at each pixel, you have the brightness value at that point. And so instead of just seeing an image, a computer really gets a million numbers in a grid that tell you the brightness values at all the positions.
The matrix, if you will. It really is the matrix.
Yeah. And so we have to go from that grid of pixels and brightness values into high-level concepts like iguana and so on. And as you might imagine, this iguana has a certain pattern of brightness values. but iguanas actually can take on many appearances. So they can be in many different appearances, different poses, in different brightness conditions, against different backgrounds. You can have different crops of that iguana. And so we have to be robust across all those conditions, and we have to understand that all those different brightness patterns actually correspond to iguanas. Now, the reason you and I are very good at this is because we have a massive neural network inside our heads that is processing those images. So light hits the retina, travels to the back of your brain to the visual cortex, and the visual cortex consists of many neurons that are wired together and that are doing all the pattern recognition on top of those images. Over the last, I would say, about 5 years, the state-of-the-art approaches to processing images using computers have also started to use neural networks, but in this case, artificial neural networks. But these artificial neural networks, and this is just a cartoon diagram of it, are a very rough mathematical approximation to your visual cortex. We really do have neurons, and they are connected together. And here I'm only showing 3 or 4 neurons in 4 layers. But a typical neural network will have tens to hundreds of millions of neurons, and each neuron will have 1,000 connections. So these are really large pieces of almost simulated tissue. And then what we can do is we can take those neural networks and we can show them images. So for example, I can feed my iguana into this neural network, and the network will make predictions about what it's seeing. Now, in the beginning, these neural networks are initialized completely randomly. So the connection strengths between all those different neurons are completely random. So it might think that you're actually looking at a boat right now, and it's very unlikely that this is actually an iguana. And during the training process, really what we're doing is we know that that's actually an iguana. We have a label. So what we're doing is we're basically saying we'd like the probability of iguana to be larger for this image and the probability of all the other things to go down. And then there's a mathematical process called backpropagation and stochastic gradient descent that allows us to backpropagate that signal through those connections, update every one of those connections just a little amount, and once the update is complete, the probability of iguana for this image will go up a little bit, so it might become 14%, and the probability of the other things will go down. And of course, we don't just do this for this single image. We actually have entire large data sets that are labeled. So we have lots of images. Typically, you might have millions of images, thousands of labels, or something like that. And you are doing forward-backward passes over and over again. So you're showing the computer, here's an image, it has an opinion, and then you're saying this is the correct answer, and it tunes itself a little bit. You repeat this millions of times. And sometimes you show images, the same image to the computer, hundreds of times as well. So the network training typically will take on the order of a few hours or a few days, depending on how big of a network you're training. And that's the process of training a neural network. That they really do require a lot of these examples, and they really do start from scratch. They know nothing, and it's really hard to wrap your head around this. So as an example, here's a cute dog, and you probably may not know the breed of this dog, but the correct answer is that this is a Japanese Spaniel. Now, all of us are looking at this, and we're seeing Japanese Spaniel, and we're like, okay, I got it. I understand kind of what this Japanese Spaniel looks like. And if I show you a few more images of other dogs, you can probably pick out other Japanese Spaniels here. So in particular, those 3 look like a Japanese Spaniel, and the other ones do not. So you can do this very quickly, and you need one example, but computers do not work like this. They actually need a ton of data of Japanese Spaniels. So this is a grid of Japanese Spaniels, showing them, you need thousands of examples, showing them in different poses, different brightness conditions, different backgrounds, different crops. You really need to teach the computer from all the different angles what this Japanese Spaniel looks like, and it really requires all that data to get that to work. Otherwise, the computer can't pick up on that pattern automatically.
Where is Andre going with this?
About the setting of self-driving. Of course, we don't care about dog breeds too much. Maybe we will at some point. But for now, we really care about lane line markings, objects, where they are, where we can drive, and so on. So the way we do this is we don't have labels like iguana for images, but we do have images from the fleet like this, and we're interested in, for example, lane line markings. So a human typically goes into an image, and using a mouse annotates the lane line markings. So here's an example of an annotation that a human could create, a label for this image. And it's saying that that's what you should be seeing in this image. These are the lane line markings. Only tool in the toolbox that we have is labeled data. So what we do is we need to take images like this when the network fails, and we need to label them correctly. So in this case, we will turn the lane to the right. And then we need to feed lots of images of this to the neural net. And neural net, over time, will basically pick up on this pattern that those things there don't matter, but those lane line markings do, and we'll learn to predict the correct lane.
I don't know about you, but damn, this looks like a hard-ass problem. This is a Herculean task, but I guess the mission is greater than my sanity.
A number of people have kind of pointed out that potentially we could use simulation to actually achieve the scale of the data sets, and we're in charge of a lot of the conditions here, and maybe we can achieve some variety in a simulator. Now, at Tesla, this is actually a screenshot of our own simulator. We use simulation extensively. We use it to develop and evaluate the software. We've also even used it for training, quite successfully so. But really, when it comes to training data for neural networks, there really is no substitute for real data.
I hope Tesla's putting that data to work, considering they have the most data in the world combined, talking about real-world driving experience.
The simulations have a lot of trouble with modeling appearance, physics, and the behaviors of all the agents around you. So here are some examples to really drive that point across. The real world really throws a lot of crazy stuff at you. So in this case, for example, we have very complicated environments with snow, with trees, with wind. We have various visual artifacts that are hard to simulate potentially. We have complicated construction sites, bushes, complicated construction sites that might feature lots of people, kids, animals, all mixed in, and simulating how those things interact and flow through this construction zone might actually be completely intractable. It's not about the movement of any one pedestrian in there, it's about how they respond to each other, and how those cars respond to each other, and how they respond to you driving in that setting. And all of those are actually really tricky to simulate. And in some cases, it's not even that you can't simulate it, it's that you can't even come up with it.
Yeah.
So for example, I didn't know that you can have truck on truck on truck like that, but in the real world, you find this, and you find lots of other things that are very hard to really even come up with. So really, the variety that I'm seeing in the data coming from the fleet is just crazy with respect to what we have in a simulator. We have a really good simulator.
Simulation, you're fundamentally grading your own homework. So if you know that you're going to simulate it, okay, you can definitely solve for it. But as Andre is saying, you don't know what you don't know. The world is very weird and has millions of corner cases.
Millions upon millions of corner cases.
I think the 3 points that I really tried to drive home until now are, to get neural networks to work well, you require these 3 essentials. You require a large data set, a varied data set, and a real data set. Mm-hmm. And if you have those capabilities, you can actually train neural networks and make them work very well. And so why is Tesla in such a unique and interesting position to really get all these 3 essentials right? And the answer to that, of course, is the fleet. We can really source data from it and make our neural network systems work extremely well. So let me take you through a concrete example of, for example, making the object detector work better, to give you a sense of how we develop these neural networks, how we iterate on them, and how we actually get them to work over time. So object detection is something we care a lot about. We'd like to put bounding boxes around, say, the cars and the objects here, because we need to track them and we need to understand how they might move around. So again, we might ask human annotators to give us some annotations for these, and humans might go in and might tell you that, okay, those patterns over there are cars and bicycles and so on. And you can train your neural network on this, but if you're not careful, the neural network will make mispredictions in some cases. So as an example, if we stumble by a car like this that has a bike on the back of it, then the neural network actually, when I joined, would actually create 2 detections. It would create a car detection and a bicycle detection. And that's actually kind of correct, because I guess both of those objects actually exist. But for the purposes of the controller and the planner downstream, you really don't want to deal with the fact that this bicycle can go with the car. The truth is that that bike is attached to that car, so in terms of like just objects on the road, there's a single object, a single car. So the process that we go through internally in the team is that we take this image, or a few images that show this pattern, and we have a mechanism, a machine learning mechanism, by which we can ask the fleet to source us examples that look like that. Now, the fleet doesn't just respond with bicycles on backs of cars. We look for lots of things all the time. So, for example, we look for boats, and the fleet can respond with boats. We look for construction sites, and the fleet can send us lots of construction sites from across the world. We look for even slightly more rare cases. So, for example, finding debris on the road is pretty important to us. So these are examples of images that have streamed to us from the fleet that show tires, cones, plastic bags, and things like that. To summarize, the process by which we iterate on neural network predictions looks something like this. We start with a seed data set that was potentially sourced at random. We annotate that data set, and then we train neural networks on that data set and put that in the car. And then we have mechanisms by which we notice inaccuracies in the car when this detector may be misbehaving. And so we refer to this iterative process by which we improve these predictions as the data engine. So iteratively deploying something, potentially in shadow mode, sourcing inaccuracies, and incorporating them into the training set over and over again. And we do
Wash, rinse, repeat, millions of times over multiple years. Now, I don't know about you, given enough time, the machine's going to become better than we ever possibly could, because it's going to have more experiences, than we ever possibly could. In that situation, who do you trust? The neural net that's had lifetimes of experiences, or yourself after a long day of work, play, drinking, what have you? I know my answer.
Really, to utilize the power of the fleet, you don't want to go through this human annotation bottleneck. You want to just stream in data and automate it automatically. And we have multiple mechanisms by which we can do this. So as one example of a project that we recently worked on is the detection of cut-ins. So you're driving down the highway, someone is on the left or on the right, and they cut in front of you into your lane. So here's a video showing the autopilot detecting that this car is intruding into our lane. And we can use that for training the neural net. And so the neural net will automatically pick up on a lot of these patterns. So for example, the cars are typically yawed. They're moving this way. Maybe the blinker is on. All that stuff happens internally inside the neural net just from these examples. So we asked the fleet to automatically send us all this data. We can get 500,000 or so images, and all of these would be annotated for cut-ins, and then we trained the network. And then we took this cut-in network and we deployed it to the fleet, but we don't turn it on yet. We run it in shadow mode. And in shadow mode, the network is always making predictions. Hey, I think this vehicle is going to cut in from the way it looks. This vehicle is...
Damn! Shadow mode is FSD's superpower. When ready, you flip the switch and the car is better today than it was yesterday. This is 4 years ago, people. What is the software like today? What will it be like in 5 years? Pipe down, cash register. Class is still in session.
This is a clip that we had from shadow mode of the cut-in network. And it's kind of hard to see, but the network thought that the vehicle right ahead of us on the right was going to cut in. And you can sort of see that it's slightly flirting with the lane line. It's sort of encroaching a little bit. And the network got excited and it thought that that was going to be cut in. That vehicle will actually end up in our center lane. That turns out to be incorrect, and the vehicle did not actually do that. So what we do now is we just churn the data engine. We source that ran in the shadow mode, is making predictions. It makes some false positives, and there are some false negative detections. So we got overexcited and sometimes we missed a cut-in when it actually happened. All those create a trigger that streams to us, and that gets incorporated now for free. There's no humans harmed in the process of labeling this data. Incorporated for free into our training set. We retrain the network and redeploy the shadow mode. And so we can spin this a few times, and we always look at the false positives and negatives coming from the fleet. And once we're happy with the false positive, false negative ratio, we actually flip the bit and actually let the car control to that network.
Damn! Good luck trying to catch up with Tesla with every one of their vehicles sending data back to their fleet. This is a race where no other autopilot full self-driving technology can win other than Tesla, simply because of the advantage Tesla has with the fleet.
Everyone's training the network all the time is what it amounts to. Whether autopilot is on or off, the network is being trained. Every mile that's driven for the car that's hardware 2 or above is training the network.
Another interesting way that we use this in the scheme of fleet learning, and the other project that I will talk about, is path prediction. So while you are driving the car, what you're actually doing is you are annotating the data because you are steering the wheel. You're telling us how to traverse different environments. So what we're looking at here is some person in the fleet who took a left through an intersection. And what we do here is we have the full video of all the cameras, and we know that the path that this person took because of the GPS, the inertial measurement unit, the wheel angle, the wheel ticks. So we put all that together, and we understand the path that this person took through this environment.
The crazy thing is, the network is predicting paths it can't even see with incredibly high accuracy. It can't see around the corner, but it's saying the probability of that curve is extremely high. So that's the path. And it nails it. You will see that in the cars today. We're going to turn on augmented vision so you can see the lane lines and the path predictions of the cars overlaid on the video.
Yeah. There's actually more going on under the hood that you can even tell.
I mean, it's kind of scary, to be honest. Yeah.
He ain't lying. That is real scary, but it works. I don't know how the sausage made. Hell, I'll never know how the sausage is made. But you can go ahead and put that down on the bun for me, please, and thank you.
A lot of details I'm skipping over. You might not want to annotate all the drivers. You might want to just imitate the better drivers, and there's many technical ways that we actually slice and dice that data. But the interesting thing here is that this prediction is actually a 3D prediction that we project back to the image here. So the path here forward is a 3-dimensional thing that we're just rendering in 2D. But we know about the slope of the ground from all of this, and that's actually extremely valuable for driving. So what I talked about so far is really the three key components of how we iterate on the predictions of the network and how we make it work over time. You require a large, varied, and real data set. We can really achieve that here at Tesla. And we do that through the scale of the fleet, the data engine, shipping things in shadow mode, iterating that cycle, and potentially even using fleet learning where no human annotators are harmed in the process, and just using data automatically, and we can really do that at scale. So in the next section of my talk, I'm going to especially talk about depth perception using vision only. So you might be familiar that there are at least two sensors in the car. One is vision, cameras, just getting pixels, and the other is LiDAR that there are a lot of companies also use. And LiDAR gives you these point measurements of distance around you. Now, one thing I'd like to point out, first of all, is you all came here, you drove here, many of you, and you used your neural net and vision. You were not shooting lasers out of your eyes, and you still ended up here.
We might have.
So things went well.
Can't speak for everyone.
So clearly, the human neural net derives distance and all the measurements and the 3D understanding of the world just from vision. It actually uses multiple cues to do so. I'll just briefly go over some of them, just to give you a sense of roughly what's going on inside. As an example, we have two eyes pointed out, so you get two independent measurements at every single time step of the world ahead of you, and your brain stitches this information together to arrive at some depth estimation because you can triangulate any points across those two viewpoints. A lot of animals, instead, have eyes that are positioned on the sides, so they have very little overlap in their visual fields, so they will typically use structure from motion, and the idea is that they bob their heads, and because of the movement, they actually get multiple observations of the world, and you can triangulate, again, depths. And even with one eye closed and completely motionless, you can still have some sense of depth perception. If you did this, I don't think you would notice me coming 2 meters towards you or 100 meters back, and that's because there are a lot of very strong monocular cues that your brain also takes into account. This is an example of a pretty common visual illusion where you have, these two blue bars are identical, but your brain, the way it stitches up this scene, is it just expects one of them to be larger than the other because of the vanishing lines of this image. So your brain does a lot of this automatically. So here's a video going down, I think this is San Francisco, of a Tesla. So these are our cameras, our sensing, and we're looking at I'm only showing the main camera, but all the cameras are turned on, the 8 cameras of the autopilot. And if you just have this 6-second clip, what you can do is you can stitch up this environment in 3D using multi-view stereo techniques. So this is the 3D reconstruction of those 6 seconds of that car driving through that path. And you can see that this information is very well recoverable from just videos. And roughly that's through process of triangulation and, as I mentioned, multi-view stereo. And we've applied similar techniques, slightly more sparse and approximate, also in the car. So in circles, I'm showing radar objects. And the cuboids that are coming out here are purely from vision. So the cuboids here are just coming out of vision, and the depth of those cuboids is learned via sensor annotation from the radar. So if this is working very well, then you would see that the circles in the top-down view would agree with the cuboids, and they do. And that's because neural networks are very competent at predicting depths. They can learn the different sizes of vehicles internally, and they know how big those vehicles are, and you can actually derive depth from that quite accurately. This approach is called self-supervision. So what you do in a lot of these papers is you only feed raw videos into neural networks with no labels whatsoever, and you can still get neural networks to learn depth.
What?
And it's a little bit technical, so I can't go into the full details, but the idea is that the neural network predicts depth at every single frame of that video, and then there are no explicit targets that the neural network is supposed to regress to with the labels, but instead, the objective for the network is to be consistent over time. So whatever depth you predict should be consistent over the duration of that video, and the only way to be consistent is to be right. In summary, people drive with vision only, no lasers are involved. This seems to work quite well. The point that I'd like to make is that visual recognition, and very powerful visual recognition, is absolutely necessary for autonomy. It's not a nice to have. Like, we must have neural networks that actually really understand the environment around you. And LiDAR points are a much less information-rich environment. So vision really understands the full details. Just a few points around there's much less information in those. Is that a plastic bag or is that a tire? A LiDAR might just give you a few points on that, but vision can tell you which one of those two is true, and that impacts your control. Is that person who is slightly looking backwards, are they trying to merge into your lane on the bike, or are they just going forward? In the construction sites, what do those signs say? How should I behave in this world? The entire infrastructure that we have built up for roads is all designed for human visual consumption. So all the signs, all the traffic lights, everything is designed for vision. And so that's where all that information is, and so you need that ability. Is that person distracted and on their phone? Are they going to walk into your lane? Those answers to all these questions are only found in vision and are necessary for level 4, level 5 autonomy.
Ding, 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 ding! Tell him what he's won, Johnny! You're motherfucking right. Vision is absolutely necessary if we're talking about level 4, level 5 autonomy. And not just 20/20 vision, it needs to be superhuman. That's where the neural nets come in. As Elon is fond of saying, LiDAR is a fool's errand. It's a crutch.
And that is the capability that we are developing at Tesla. And this is done through combination of large-scale neural network training, through data engine and getting that to work over time, and using the power of the fleet. And so in this sense, LiDAR is really a shortcut. It sidesteps the fundamental problems, the important problem of visual recognition that is necessary for autonomy. And so it gives a false sense of progress and is ultimately a crutch. So if I was to summarize the entire, my entire talk in one slide, it would be this. All of autonomy, because you want level 4, level 5 systems that can handle all the possible situations in 99.99% of the cases. And chasing some of the last few nines is going to be very tricky and very difficult, and is going to require a very powerful visual system. And so the rate of progress at which you can actually address these problems, iterate on the software, and really feed the neural networks with the right data, that rate of progress is really just proportional to how often you encounter these situations in the wild. And we encounter them significantly more frequently than anyone else, which is why we're going to do extremely well.
Which is why they're going to win. No one else has the fleet, so therefore no one else has a chance to do this before Tesla can get it done. They have the most brilliant minds tackling these problems 4 years ago and are now presented a gift with artificial intelligence as a catalyst to propel us into the future we all hope to see.
It's all super impressive. Thank you so much. How much data, how many pictures are you collecting on average from each car per period of time? And then it sounds like the new hardware with the dual active computers gives you some really interesting opportunities to run in full simulation one copy of the neural net while you're letting the other one drive the car and compare the results to do quality assurance. And then I was also wondering if there are other opportunities to use the computers for training when they're parked in the garage for the 90% of the time that I'm not driving my Tesla around. Thank you very much.
Yep. So for the first question, how much data do we get from the fleet? So it's really important to point out, it's not just the scale of the data set, it really is the variety of that data set that matters. If you just have lots of images of something going forward on the highway, at some point the neural net just gets it. You don't need that data. So we are really strategic in how we pick and choose, and the trigger infrastructure that we've built up is quite sophisticated and allows us to get just the data that we need right now. And so it's not a massive amount of data, it's just very well picked data. For the second question, with respect to redundancy, absolutely, you can run basically the copy of the network on both, and that is actually how it's designed to achieve a level 4, level 5 system that is redundant.
The car is an inference optimized computer. We do have a major program at Tesla, which we don't have enough time to talk about today, called Dojo. That's a super powerful training computer. The goal of Dojo will be to be able to take in vast amounts of data and train at a video level and do unsupervised massive training of vast amounts of video with the Dojo program.
Hello, Dojo computer. Giving them a little nugget for the first Investor AI Day. Stay tuned. We're not done with Dojo just yet.
But that's for another day.
But the one challenge that I'm curious to how you're going to solve is changing lanes. Because whenever I try to get into a lane with traffic, everybody cuts you off. And so human behavior is very irrational when you're driving in LA, and the car just wants to do it safely, and you almost have to do it unsafely. So I was wondering how you're going to solve that problem.
Yeah. So one thing I will point out is I spoke about the data engine as iterating on neural networks, but we do the exact same thing on the level of software and all the hyperparameters that go into the choices of when we actually lane change, how aggressive we are. We're always changing those, potentially running them in shadow mode and seeing how well they work. And so to tune our heuristics around when it's okay to lane change, we would also potentially utilize the data engine and the shadow mode and so on. ultimately, actually designing all the different heuristics for when it's okay to lane change is actually a little bit intractable, I think, in the general case. And so ideally, you actually want to use fleet learning to guide those decisions. So when do humans lane change, in what scenarios, and when do they feel it's not safe to lane change? And let's just look at a lot of the data and train machine learning classifiers for distinguishing when it is safe to do so. And those machine learning classifiers can write much better code than humans because they have the massive amount of data backing that. So they can really tune all the right thresholds and agree with humans and do something safe.
Well, I think we'll probably have a mode that goes beyond Mad Max mode to LA traffic mode. Yeah. Well, you know, Mad Max would have a hard time in LA traffic, I think.
Yeah, so really it's a trade-off. Like, you don't want to create unsafe situations, but you want to be assertive. But that little dance of how you make that work as a human is actually very complicated, and it's very hard to write it in code.
Yep, get rid of all that nasty code and let the computer figure it out with video input in, output actions out.
Trying to do here is almost develop consciousness in the cars through the neural network. And so I guess the challenge is, how do you not create a circular reference in terms of the pulling from the centralized model of the fleet to that handoff where the car has enough information? Where is that line, I guess, in terms of the point of the learning process to handing it off where there's enough information in the car and not having to pull from the fleet?
Well, the car can operate if it's completely disconnected from the fleet. It uploads the training that's, you know, better and better as the fleet gets better and better. So simply, if you disconnected it from the fleet, from that point onwards, it would stop getting better, but it would still function fine.
I guess I'm having a hard time reconciling how, if there was a situation where I'm driving up the hill, as you showed, and I'm predicting where the road is going to go, that's coming from all of the other fleet variables that led to that intelligence, how I'm getting the benefit of the low power using the cameras with the neural network. That's where I'm losing the two. Maybe it's just me, but I guess that's.
I mean, the compute power in the full self-driving computer is incredible, and maybe we should mention that if it had never seen that road before, it would still have made those predictions, provided it was a road in the United States.
In the case of LiDAR, the March of Nines, isn't there an example, and I want to just get to your slam on LiDAR because it was pretty clear you don't like LiDAR. In this,
LiDAR is lame. LiDAR is lame. Lame.
LiDAR is lame. LiDAR is lame. Unnecessary crutch that will ultimately prevent these other companies from actually achieving level 4, level 5 autonomy of any real magnitude.
Case where at some point 99999 down the road where actually LiDAR may be helpful, and why not have it as some sort of a redundancy or backup? So that's my first question. And the second, so you can still have your focus on computer vision, but just have it as a redundant. And my second question is, if that is true, what happens to the rest of the industry that's building their autonomy solutions on LiDAR?
Yes, indeed. What will happen to the industry for all of those individuals using LiDAR as their solution? Elon, don't be too rough with them.
They're all going to dump LiDAR. That's my prediction. Mark my words. I should point out that I don't actually super hate LiDAR as much as it may sound, but at SpaceX, SpaceX Dragon uses LiDAR to navigate to the space station and dock. Not only that, SpaceX developed its own LiDAR from scratch to do that, and I spearheaded that effort personally, because in that scenario, LiDAR makes sense, and in cars, it's friggin' stupid.
Get 'em!
It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless. So you have expensive hardware that's worthless on the car. We do have a forward radar, which is low cost and is helpful, especially for occlusion situations. So if there's like fog or dust or snow, the radar can see through that. If you're going to use active photon generation, don't use visible wavelength, because once with passive optical, you've taken care of all visible wavelength stuff. You want you want to use a wavelength that is occlusion penetrating, like radar. So LiDAR is just active photon generation in the visual spectrum. If you're going to do active photon generation, do it outside the visual spectrum in the radar spectrum. So like at 3.8 millimeters versus 400 to 700 nanometers, you're going to have much better occlusion penetration, and that's why we have a forward radar. And then we also have 12 ultrasonics for near field information, in addition to the 8 cameras and the forward radar. You only need the radar in the forward direction because that's the only direction you're going real fast. So I mean, we've gone over this multiple times. Like, are we sure we have the right sensor suite? Should we add anything more? No.
As a matter of fact, they didn't add any more. They started taking them up. Superhuman vision system is all you really need. And now that we've got the neural nets, video input in, output actions out. These cars are already driving better than humans, but they're going to be safer than the average human by an order of magnitude in no time.
It sounds like the cars are doing some computation to determine what kind of information to send back to you. Is that a correct assumption? And are they doing that in real time, or are they doing based on stored information?
Yep. So they absolutely do computation in real time on the car. And we have a way to basically specify condition that we're interested in. And then those cars do that computation there. If they did not, then we'd have to send all the data and do that offline in our backend. We don't want to do that. So all that computation happens on the car.
Damn!
On that question, it sounds like you guys are in a really good position to have currently 500,000 cars, in the future potentially millions of cars that are essentially computers representing almost free data centers for you to do computational. Is that a huge future opportunity for Tesla?
It's current.
A current opportunity, and that's not really factored in for anything yet. That's incredible.
You're damn right, cash register. Someone is getting it. Future opportunity. Nah, bruh. This is a current opportunity. And Tesla is taking full advantage.
You have these sort of network of millions of computers, which is like massive data centers, essentially, that are distributed data centers for computational capacity. Do you see it being used for other things besides self-driving in the future?
I suppose it could possibly be used for something besides self-driving. We've been super focused on self-driving, so as we get that really nailed, maybe there's going to be some other use for millions and then tens of millions of computers with hardware 3 or full self-driving computer. Yeah, maybe there would be.
Maybe there will be.
I own a Model 3 in Minnesota where it snows a lot. Since camera and radar cannot see road markings through snow, what is your technical strategy to solve this challenge? Does it involve high precision GPS at all?
Actually, like today, Autopilot will do a decent job in snow, even when lane markings are covered. Even when lane markings are faded, covered, or when there's lots of rain on them, we still seem to drive relatively well. We didn't specifically go after snow yet with our data engine, but I actually think this is completely tractable, because in a lot of those images, even when things are snowy, when you ask a human annotator, where are the lane lines, they actually could tell you. They actually are relatively consistent in creating those lane lines. As long as the annotators are consistent on your data, then the neural network will pick up on those patterns and will do just fine. So it's really just about, is the signal there, even for the human annotator? If the answer to that is yes, then the neural network can do it just fine.
Yeah, there's actually, there are a number of important signals, as Andre was saying. So lane lines are one of those things, but one of the most important signals is drive space. So what is drivable space and what is not drivable space? What actually really matters the most is drivable space more than lane lines. And the prediction of drivable space is extremely good. And I think especially after this upcoming winter will be incredible. It's like, it will be like, how could it possibly be that good? That's crazy.
Solving for autonomy is like a huge maze. You don't know where the center of the maze is, so you're just going down, taking lefts, right. Will this work? Can this work? Until you get to a dead end at the end of that maze and you're like, holy shit, can't go any further. We gotta back this up. There is a center to the maze. It's just going to be a complicated process of picking which path to follow. Just like Elon says, everyone's gonna eventually drop that damn LiDAR or perish at the end of a dead-end maze. Wall-to-wall neural networks. We know today that FSD beta can traverse roundabouts and various other nuanced driver situations. Parking lots have come a long way. I personally have a few qualms with some of the areas around construction and using the toll roads, but I have great confidence that these situations will be ironed out. That's all for class today. This is part 2 of the birth of Tesla's FSD computer. If you missed part 1, make sure you check that out. It will be one of the videos in the end screen. Join me for class next Thursday as we will get into part 3, the software side of things. My office hours in the comments below. Be easy.